going to be chairing the next session. We're going to have two talks. And the first one coming in is David Mross for the Weizmann Institute. And I'm just going to let him tell you the title of his talk. Okay, thank you, David.
All right. Can everyone hear me and see my slides?
Yes, looks good.
All right, great. Just a second. That's not what I wanted. Okay, perfect. Yeah, so thank you very much for putting together this very nice conference with all the quantum Hall experts. And I'm very excited to talk here today about some of my later results on thermal and charge transport at the filling factor 5.5, and specifically on how they may or may not be able to tell us what phase is actually realized at this filling factor. So, given the expert audience, I'll have a very brief introduction just to warm us all up for what we're talking about. So the filling factor 5.5, there's been a plateau which has first been observed probably 35 years ago by now. And despite this long time, there's actually still a lot of mysteries, including what phase describes this plateau. So one of the few things, I guess, that's fairly uncontroversial is that this is related to pairing. And in some sense. So the cartoon picture is that I have two completely filled Landau levels. They are pretty much dead. And I have one partially filled Landau level. And on the single particle picture, I have this huge degeneracy here, which will be lifted by interactions. And to organize what happens, a standard approach is to introduce the notion of a composite fermion, such that in this half-filled Landau level, I have these composite fermions which experience an average magnetic flux which vanishes, and therefore these composite fermions can either form a composite Fermi C, or they can pair up to form a composite Fermi superconductor, which would amount to an incompressible quantum Hall state. So that's the uncontroversial part. Now the big question is, what's the pairing channel? So what we have essentially is fermions or single species, and without any symmetry. So there's an infinite number of possible pairing channels that may be realized. So this classification is integers, and this integer can easily be viewed as the number of Majorana modes that encircle a finite size sample at the edge. So here my notation is that the outer guys, they're just electronic edge channels. This guy in the middle, that's a nu equals 1/2 edge channel. Together, they make up the Hall conductance to be 5.5, which is the same for all these possible states. But in addition, there are these n neutral Majorana fermions, and they generically affect the Hall conductance. And specifically, there's a quantized value that the thermal Hall conductance should be 3, which is the contribution from the charge-carrying modes, and then 1/2 times the number of Majorana modes, with the convention that a negative value corresponds to a Majorana that counterpropagates. So amongst all these many n's, not all are equal, some are kind of special. So they are for historical reasons. Some of them have names, like the most famous one is n equals 1, which is the Morid-Pfaffian state. Then there's some years later, its particle Hall conjugate, the anti-Pfaffian was found, and then there are additional states which were discussed more recently, in particular the particle Hall symmetric Pfaffian, which was discussed by Son in the context of particle Hall symmetry in this Landau level. So this particle Hall symmetry is kind of an important player. So let me just remind you how one can see that this particular phase may be particle Hall symmetric and the other ones are not. So if I have some quantum Hall state at 5.5, so I have my fractional mode over here, I have my neutral modes over here, and I'm taking the boundary between 5.5 and 2 to avoid the integer modes, which are not that interesting. And to get the particle Hall conjugate edge, I'm replacing the empty Landau level over here by a filled Landau level. So I'm considering the boundary between nu equals 5.5 and nu equals 3. So at this point, I have two counterpropagating charge modes over here, the fractional 1/2 charge mode and the integer mode like this. And so what I can just do, and firstly, there's a simple change of basis to a mode which doesn't carry charge and to a mode which does carry charge. So in terms of bulk excitation, this corresponds to having a new charge mode, which is an electron times the old semyon, and a neutral fermion, which is an electron times a square of the old semyons. And if I just write this out, I'm getting a new edge, which has a fractional charge mode, just like I started with. And it has, again, some number of my runner modes. In this case, I have minus n plus 2, the n which I started with, and 2 from this kind of change of basis. And they now propagate in the opposite direction over here, this n plus 2 modes compared to the charge mode. So in other words, under this particle hole conjugation, the integer n that I started with becomes minus n minus 2, or like so. And this has a specific value, n being minus 1, under which it maps onto itself and the particle hole symmetric. Or, the edge structure at least is particle hole symmetric in this sense. Now, one sort of more subtle point about this is that in many cases under experimental conditions, such as not having a fully pristine edge but having randomness, the charge mode and the runner mode actually tend to decouple. So one can really view this kind of reconstructed edge as having just one mode carrying all the charge, which is more or less decoupled from all the neutral sectors. So under this transformation, the pH Pfaffian phase maps onto itself, whereas the Pfaffian maps onto the anti-Pfaffian, and the similar holds for all the other possible integers. Now, there's been lots of numerical experiments on this state for, ranging back to more than 20 years. And they all agree that both the Pfaffian and the anti-Pfaffian are very good trial states, or very likely ground states in the case of Coulomb interactions. So it's either Pfaffian or anti-Pfaffian, because many of the early experiments had manifest particle hole symmetry, so they cannot distinguish which of them is actually realized. Now, more recently, there have been numerics that do include effects of mixing between the Landau levels and thereby break particle hole symmetry. And some of them seem to find that the Pfaffian does better, and some of them that the anti-Pfaffian does better. So maybe there's a slight balance is slightly tipped in favor of the anti-Pfaffian, but it's a pretty close thing. Now, in complete contrast, there's been an experiment which tried to directly measure the terminal Hall effect. So it's been out about 3 years ago. So it's actually a 2-terminal measurement, but nevertheless, it can tell us probably quite a lot. And it finds a value which is 5/2, which corresponds to the integer -1, which is neither the Pfaffian nor the anti-Pfaffian, but it's this value that is consistent with particle hole symmetry. So it suggests a pH Pfaffian phase. In addition, there's been a more recent experiment which measured thermal upstream noise. So if I have such an edge and I measure thermal noise going to the upstream direction, I expect that the number of my runner fermions must be negative. So there needs to be some neutral mode which propagates in the opposite direction to the charge mode. Now, the same experiment also measured this edge, and it again found upstream noise. So which means in this case that -n plus 2 must also be negative. And if you take these two things together, you again find that it supports the pH Pfaffian, or the value n equals -1 as a ground state. And this is kind of a big kind of clash between what numerics finds and has been finding for some 2 decades and what these more recent experiments seem to find. And this clash, this conflict has been extremely fruitful in terms of a lot of theoretical work primarily. And so there's been a lot of studies considering what happens at the edge about equilibration. Can equilibration account for the measured value, since it's a 2-terminal measurement after all, and the ground state may actually be one of the other phases instead. How is noise generated, and can the generation of noise can distinguish between these phases? So all these kind of questions arise naturally out of this conflict. And in parallel, there have been studies of bulk physics, such as how does this order affect these different phases, may domain walls form, and these kind of questions. And finally, there's been a set of studies which one may term as why not pH Pfaffian. It seems like we have a very good state as a matter of principle. It's particle hole symmetric, which is nice. It's a symmetry which may even be approximately realized, but for some reason it doesn't, numerics, one never finds it. And moreover, we don't even have a satisfactory trial wave function or any Hamiltonian, realistic or not, to realize this phase. So there have been some suggestions that there may be more fundamental problems with this pH Pfaffian as a phase. There's been lots of interesting stuff going on, and I'll be mainly talking about these two regions. Firstly, a work about the bulk effect, and finally, a little bit of what may happen at the edge. So specifically, I'll be talking about this work I've been involved in together with Cosma from Leipzig, my colleagues at Weizmann, and Sascha Mirlin from Karlsruhe. And this work is motivated by earlier works, both by myself and these other works that came out in parallel, about how disorder may affect the measured terminal Hall conductance. So these works are mainly based by the numerics, on the numerics, which say both the anti-Pfaffian and the Pfaffian are very good. So these are good, good ground states for the interactions that we expect. So maybe, since they're so close in energy, disorder that's naturally there in a sample may locally tip the balance and favor one of these phases over the other ones. And so if that were to happen, then you get regions in space where you have, say, the anti-Pfaffian phase separated by regions with the Pfaffian phase, and each such island would be encircled by 4 Majorana modes to make up the difference in integers between n equals 1 and n equals 3. So there's been, follow-up studies on whether this may happen energetically and so on. But for now, I'll just explore what happens if this is indeed the case. So we have these 4 Majorana modes, and if I now have a phase transition between a configuration where the majority is Pfaffian and the majority is anti-Pfaffian, then 4 Majorana fermions need to delocalize in the bulk. So that's like a multi-critical point, a phase transition where 4 Majoranas change from one topological phase to a different topological phase. And one may generically expect that such a multi-critical point will be split, since we have no extra symmetry, into a sequence of phase transitions. And if this were to happen, then there would be an intermediate phase which with a terminal Hall conductance in agreement with the one that the experiment finds. Oops, I think I made a mistake. But this is not quite the end of the story, as all these works already recognized. Namely, there's something special about this, filling factor 5½ in the sense that we have pairing between these composite fermions, which means that we have a superconducting symmetry class, or we have particle hole symmetry, where we may have interference between particles and holes that scatter on some disorder configuration. And this interference is such that there's weak anti-localization. So there is actually no guarantee that we'll have a localized phase at all, and instead there may be a metallic phase, which has been previously proposed and described as thermal metal, where the terminal Hall conductance would not be quantized. So the similar phase diagrams were also worked out in these other papers, and they all mentioned this terminal metal phase. So now I want to talk a bit more today about actually what's going on in this terminal metal phase. And to what extent is it true that this kappa xy is really not quantized at all? It certainly has no reason to be perfectly quantized, but we'll see that it may actually be approximately so. So the crucial point about this particle hole symmetry, in contrast to other symmetries that we often encounter, is that it's only really present in specific part of the spectrum. So the relate state that energy, positive energy and negative energy. So close to zero energy, we have a symmetry, but soon as we are far away from zero energy, we have no knowledge that we are supposed to be symmetric, because the states that we are symmetric with are kind of far away. So what this means more specifically is if I have a particle at some energy which follows some random trajectory in my disorder, and it wants to interfere with a hole which has a similar trajectory, and there's a phase factor depending on the energy. And this phase factor, if this is of order unity, then the interference is going to get canceled. So we lose the weak anti-localization, and instead we get the next leading effect, if you don't have symmetries, which is the standard weak localization in the quantum Hall symmetry class. Right, so what we have is we have some energy window where we have anti-localization at small energies, and then at bigger energies we have localization. What that means for the thermal conductance is the following. So thermal conductance involves states in some energy window between plus and minus t. And now it depends on the order of limits what's going on. So if we keep our temperature finite, so it's here, blue is supposed to denote temperature, and I'm making my system larger and larger at finite temperature, then the window where I have delocalized states will shrink. So it will almost not contribute to the thermal conductance, and I get a thermal conductance which goes to 0. Now I can go to the opposite limit, where I'm taking kind of temperature to 0. And in this case, all of the states that contribute to my thermal conductance are actually delocalized, and I'm getting metallic behavior. I'm going to get a divergent conductance. Right, so it's it depends on which limit here we're in. And this raises the possibility that, well, if raising the temperature at fixed system size, the thermal conductance may go down. And as a consequence, one may expect that actually the thermal Hall conductance, even if it's not or poorly quantized at the lowest temperatures, may become better quantized as we increase the temperature. That's the basic premise. And to test for this, we just took a kind of a toy model, simple lattice model, where we could perform free fermion numerics to see what's going on. So this lattice model is a model of Majorana fermions hopping on a honeycomb model with both nearest and next nearest neighbor hopping. So you may recognize it as a famous Haldane honeycomb model. If you don't have next neighbor couplings, then the model is gapless and has some extra symmetry. And if we turn on this extra coupling over here, then we may get a topological phase distinct by the sign of this coupling constant sitting here. And so if we can see, for example, on a finite size geometry that there are edge states in the gapped phases. So that's our starting point. And to connect this to the question that we're interested in, the quantum Hall case, I would say that very loosely you can view the two gap topological phases as a Pfaffian and anti-Pfaffian. Those are the phases, the only phases that are present in the clean system. And an extra symmetry corresponds to the case of particle hole symmetry, where we corresponding to the pH Pfaffian. So that's roughly the way to think about it. So we take the system, and the first thing we do is we just at this order, we make both these coupling constants random, and then see how the transmission through the sample, the longitudinal transmission, or if it's the same as the dimensionless conductance, changes. And if it's a thermal metal, we want to see anti-localization. And indeed, that's what we find at some disorder strengths at this value, along the symmetric value, we find a conductance which fits fairly well the expected weak anti-localization behavior. Now, we can take this disorder strength and kind of fix it, right? So we have, again, the transition between a topological phase with a fixed Chern number to this thermal metal phase to the opposite Chern number. And now as a function of energy, that's what we find. So the thermal metal dies very, very quickly. And we immediately get a new insulating state, this case with 0 Chern number, which in the quantum Hall analogy would correspond to the 5-half case. So that's the function of energy, and one can indeed follow this the crossover between weak anti-localization and weak localization as a function of energy. So for low energies, we see that the smallest system has the smallest transmission probability, and at larger energies, it reverses, and the smallest system transmits the best. So that's the expected crossover between the two regimes that I was referring to. Okay, I'll skip over this because it's not super important. One can, of course, fit the crossover function, and again, it works out reasonably well. And the localization length, which follows from this, is has this important feature that it's not just a kind of simple power law, which you'd expect, say, from diffusion, but it has this exponential to the log squared factor, which will dominate everything that happens at the lowest energies. That will be important. So basically, this model, this toy model that we have, it has all the expected properties of a thermal metal phase. And now we want to just compute what is the actual thermal conductance and thermal Hall conductance of this model, and does it agree with this basic intuition we started with. So this calculation is fairly standard. We take a 6-terminal geometry. We use the Landauer formula, and we use it to extract the thermal conductance and the thermal Hall conductance in the usual way. So this is what we find. So the first we point the data without dashes. That's the 0 temperature data. And here we see, as expected from before, we have 0 longitudinal conductance in the topological phase. Then we have a regime of thermal metal where the conductance gets fairly large. And then we go back to the opposite topological phase as we tune ourselves past the symmetric point. And again, as expected, at the same time, the thermal Hall conductance, it starts out at the value -½ which corresponds to topological phase. Then it just evolves smoothly all the way across until it takes the opposite value in the opposite topological phase. But then, if we evaluate the same quantities at finite temperature, like this, we find that the thermal metal dies. We can already expect that based on the energies, but okay, so now we just the temperature average thing. So it's dominated by those energies, and we indeed find a vanishing longitudinal conductivity. And at the same time, we see the development of a fairly sharp plateau with zero Hall conductivity. And so, and alternatively, you can view the same data as a function of temperature. You can see that the initial values, the 0 temperature values, may be differing by quite a fair amount. And yet, as we increase the temperature, they all become very close and approximately take on this quantized value. So the quantization of thermal conductance indeed improves on this in this picture. Now, there's, of course, an issue that we are doing studies in a free fermion calculation. And in reality, there's going to be some effect of dephasing, for example, due to phonons, which will cut off the interference effects and thereby the tendency to localize. So it's a competition between the localization lengths, which we can extract, and the dephasing lengths, which is somewhat more difficult to obtain, but it's presumably a power law in temperature. And so if we have this situation, I'm just putting all coefficients now just order 1 and plotting these functions, you can find that there's a fairly large regime where we have a weak anti-localization. So that's the regime where increasing the temperature would enhance quantization, localization over here, until eventually at the lowest temperatures, we always end up in the thermal metal phase. So at the lowest temperatures, localization length is always larger than the phasing length due to this exponential factor. Right, let me start here. So here I've just took exactly the same functions, just with a kind of factor of 1/2, and we can see that this entire regime where temperature would enhance quantization just disappears. So this effect, this temperature enhancement, is only possible if interactions are weak, and we don't, of course, know what these interactions are. So it's some microscopic parameter. So this is kind of the implication. If we take this type of phase diagram, which I discussed before, and were to extend it to finite temperature, then we may expect that the thermal metal persists up to some temperature and will then cross over into this approximately quantized regime where we have a thermal Hall conductance which looks almost as well quantized as we expect in topological phase. Okay, I'll try to use my last couple of minutes to talk about something more recent work, still unpublished, which is related to edge physics and the question of, is it possible to identify or possibly rule out the pH Pfaffian state in charge transport rather than thermal transport? So that's work by my student Misha and Adi Stern. And in this work, we are trying to use the unique property of the pH Pfaffian, which is that the direct and the whole conjugate edge are the same. So we want to consider a sample which has both those edges, and this is the kind of configuration. We have filling factors 2, 3, and 5/2, such that here we have the direct edge, and here we have the whole conjugate edge. And we're interested in charge transport, so I just label the charge currents everywhere in here. And the idea is that we have a source at some voltage and all the drains are grounded. So there's no outgoing current coming here. So these are all the charge currents that are in the game. And okay, I'll use the natural variables for the edge because my particle conjugate edge will naturally be described in terms of these new modes. So I have my charge mode, and my neutral guys. And they're related to the original current in this way, which one can, for example, read off by this transformation property between those fermions. And I might as well replace the charge current by the outgoing current because it's fully dictated by total charge conservation. So all that we really have is there's one unknown quantity, which is I out, and it's directly a slave to this neutral current, which is over here. But the neutral current may in principle be affected by interactions between these two Majoranas, which I get from rewriting the composite edge with all these n other Majoranas which were initially present. So essentially, it's a boundary condition on the neutral current. It need not be the same on the left side and on the right side. And how it changes or not changes across will determine the overall conductance property of the system. Okay, so the first sanity check is if I don't have any coupling to these Majoranas, well, the neutral current doesn't change. And then from this, it just follows that all the incoming current comes out at D1. And I call it a sanity check because in this limit, I've really just in a very complicated way described a situation where there's no tunneling between these two edges. There's no tunneling, there may be some interaction, but that doesn't matter. As long as electrons can't tunnel, they'll always propagate to D1. So that's what you can see. If the current doesn't change, the neutral current, then we get conductance of 1 between source and drain. Now there's essentially two cases to consider. One is that after we hybridize these Majoranas, there is less than 2 left movers. So that means that the initial n is negative. So this includes, for example, the pH Pfaffian case where n is 1, which I'm drawing here. Now in this case, we have at most a single Majorana going from right to left, and the single Majorana is incapable of transmitting a current. Right? It's a binary thing, it's a Z2 variable. So if we just have this, say, some excitation over here, some neutral excitation, will arrive with equal probability as itself or as its particle hole version. And therefore, the neutral current at the left-hand side must be strictly 0 beyond some localization length scale of this. And now I just plug this in and I find instantly that the outgoing current is exactly half of the ingoing current. So in this configuration, the charge current, which we source over here, splits equally between D2 and D1. So we find a conductance of 1/2. Now the opposite case is the one where all Majoranas co-propagate. There's, if they all co-propagate, everything is chiral. There's no chance of localizing anything. So everything remains critical. So in that case, I can just do the RG, which means I consider what happens if I lower and lower my voltage difference, which is the same thing as I'm lowering the energy of the incoming states or increasing their wavelengths. So this RG can be viewed as shrinking the top edge until it's all the way to the point, and it suffices to consider what happens at a single point. And such tunneling at the point tends to be irrelevant. We have an integer edge next to a fractional edge. We need an integer electron to tunnel, and that one is almost always irrelevant. So if it's irrelevant, then we get a full transmission of the incoming current to D1 or unit conductance. So that's the picture we have for all these integers. We either have a unit conductance or a half conductance, essentially for the particle-like and the whole-like states, and the pH Pfaffian sits over here. But I can do exactly the same thing for the particle-hole conjugate version of the setup. I'm reversing magnetic field, I'm changing nu equals 2 and nu equals 3. Everything else remains the same. And again, I'm getting either G equals 1, G equals 1/2, but the pH Pfaffian is unique in that it gets the value of G equals 1/2 in either of the two configurations. So this is maybe somewhat surprising. It looks like in such a setup, one can actually use a charge-based observable, and a pretty simple one is that, namely the source drain conductance in this configuration, to distinguish the pH Pfaffian scenario from the other ones, from other possibilities such as Pfaffian or anti-Pfaffian. Okay, so I think my time is probably up. So my summary is that firstly, this thermal metal is really difficult to rule out experimentally. It may really very well disguise the topological phase. It has a Hall response, which can be quantized quite well at non-zero temperatures, and it even has edge states. So all this transverse conductivity actually results from edge states, which are very similar to the ones you would get in a topological phase. And secondly, one can devise configurations where the difference between neutral modes directly influences charge transport. and possibly distinguish between the different 5-half phases, with the caveat that all this requires that transport be phase coherent, and there may be interesting questions regarding coherence, such as, maybe one could use interferometry to avoid these constraints. There may be interesting questions on what's the charge noise in such setups, or different device configurations altogether. Okay, thank you.
Thank